Hello and welcome to today's lecture. In the last couple of lectures, we have discussed about various transmission media. Now, we shall focus on the signal that we shall transmit through the communication media. And today we shall discuss about transmission of digital signal, and it is the first lecture on the transmission of digital signal. So, topic is transmission of digital signal, lecture number 1. Here is the outline of the lecture. First, I shall give a brief introduction. Then we shall discuss the important characteristics of line coding. Then popular line coding techniques such as unipolar, polar and bipolar. Then we shall consider a very important characteristic, that is the modulation rate of various codes that we shall discuss in this lecture. Then we shall compare the line coding techniques that we shall cover in this lecture. And obviously, on completion, the students will be able to explain the need for digital transmission, why digital transmission is required. They will be able to explain the basic concepts of line coding, explain the important characteristics of line coding. They will be able to distinguish among various line coding techniques such as unipolar, polar and bipolar, and they will be able to distinguish between data rate and modulation rate. Before I discuss about the transmission of digital signal, let us very quickly give an overview of the transmission media that we discussed in the last two lectures. As you remember, we discussed about two types of transmission media, the guided media and unguided media. The first few here, for example, UTP, coaxial cable, optical fiber, these three belong to the guided transmission media. On the other hand, radio, microwave, satellite and infrared, they belong to unguided transmission media. And here the first column gives you the cost comparison. Obviously, the UTP is of lowest cost, coaxial has moderate cost, optical fiber has got high cost, radio communication has got moderate cost, microwave has got high cost, satellite has got high cost, infrared has got low cost. In terms of bandwidth, as we know, UTP has got lowest bandwidth and optical fiber has got the highest bandwidth. Then so far as the unguided media is concerned, microwave gives you the highest bandwidth, and of course microwave is used in two cases. The first one is essentially terrestrial microwave and second one is satellite microwave, which gives you high bandwidth. In terms of attenuation, we find optical fiber attenuation is the lowest, and of course for microwave, as you can see, the attenuation is variable depending on the atmospheric condition, it will vary. Electromagnetic interference is high in the first two cases, UTP and coaxial cable. In case of optical fiber, it is a minimum, as you can see here it is minimum. Then for radio, that electromagnetic interference is very high. For microwave and satellite, these are also high. For infrared, it is low. So far as security is concerned, as we know, the UTP and coaxial cable is not at all secured. They are prone to eavesdropping. On the other hand, optical fiber has got very high security. Eavesdropping is very difficult. On the other hand, radio wave since it is broadcast in nature, it has got very low security. Microwave and satellite has got moderate security because it is not that easy to receive the signal of from terrestrial microwave or satellite. You have to set up an antenna, and then it will require good amount of effort. On the other hand, infrared has got high security because it is within a room. So with this background, now we shall discuss the transmission of digital signal. But before doing that, let us consider what are the various options available to you. As you know, you can have digital data and you can get it converted into digital signal by suitable encoding technique. Similarly, you can have analog data which can also be converted into digital signal by suitable encoding. Then you can have analog data which can be converted into analog signal by suitable modulation technique, as we shall discuss later in this lecture. Then we can have digital data which can be converted into analog signal by suitable modulation technique. So, these are the various options available to us. Question arises, what type of signal we should use? Is digital signal or analog signal? Or as we shall see, each of these signals has its own characteristics and features, good points and bad points. As we know, a digital signal requires a low pass bandwidth, low pass channel or transmission media, and bandwidth requirement is more. On the other hand, analog signal requires a band pass communication media or band pass channel, and most of the practical channels that we shall encounter are band pass in nature, as we shall see. So, it depends on the situation and the bandwidth available, we shall choose either digital signal or analog signal. So, in some situation and depending on the bandwidth available, we shall use digital signal, and in some other situations depending on the application and depending on the bandwidth available, we shall go for analog signal. So, we shall use both. So, in this lecture we shall start with the digital data and digital signal. And as you know, the bandwidth of the medium will play a very crucial role when we send through transmission media. And we have to match the bandwidth of the signal with the bandwidth of the transmission media, so that the signal can passes efficiently without much attenuation, without much distortion, and this will require a good encoding technique, which we shall discuss in this lecture. So, in this lecture we shall consider digital data and it is converted into digital signal, and the technique that is being used is known as line coding. So, line coding technique is used for converting digital data into digital signal, and this can be explained with the help of this simple diagram. Here you have got the digital data 10000001. This data is maybe coming from some memory of the computer or maybe stored in the digital disk, and that we shall apply to a system, or we shall do line coding which will convert it into a signal. As you can see here, you have got the signal. This signal can be transmitted through the communication media. So, line coding is the technique that we shall discuss today. And what are the important characteristics that we have to consider for line coding? Here are some of the important characteristics. First one is the number of signal levels. As we do the encoding, then the number of signal levels can remain 2, because it is binary signal, binary data. It can be coded with 2 levels, or you can do multi-level encoding. For example, here as it is shown, here your data has got 2 levels, 0 and 1, and the signal has also got 2 levels. So, 2 signal levels, one is 0 volt, one is 2A volt. That means 2A is the amplitude and 0 is the amplitude. So, it has got 2 different levels. So, here 2 data levels and 2 signal levels. So, this is an example, and another here at the bottom, as you can see, you can have 2 data levels 1 0 1 0. So, it is binary data, but it has got 3 signal levels, plus, then 0, then minus A, plus A, 0, minus A. That means positive voltage, negative voltage and 0 voltage. So, as you can see here, you have got positive A, then it has got 0 here, then it has got negative A. So, these are the three levels that is being used here for the purpose of encoding. And whenever you do multi-level encoding, as we know that information content can get changed, and as you know that I is equal to is given by b into 2b into log 2m. That means the number of signal levels that is being used will decide the information rate, where b is the bandwidth of the medium. So, you can to achieve more higher data rate, information rate, we can go for multi-level encoding if necessary. Then comes the question of bit rate versus baud rate. So, as I have explained in the last lecture, the bit rate is essentially the data rate at which the signal is transmitted. On the other hand, the baud rate is essentially the number of signaling elements. So, the number of signaling elements used can be more than the data rate, can be less than the data rate. So, if you use multi-level encoding, then the baud rate will be less than the data rate, but in some cases the baud rate can be more than the data rate. So, that we have to decide. Obviously, we shall prefer lower baud rate, and so that achieve higher data rate of transmission through the transmission media. Then comes the question of DC component. As we know, whenever we try to send signal through a transmission media, it is difficult to send DC signal because of the presence of transformers, capacitor in the equipment through which we are sending the signal. So, the because of the presence of transformer and capacitor, DC component will be blocked, that will lead to attenuation, but sometimes there will be a DC component. For example, if it is encoded in this manner, that means you have got 0 volt and say another voltage plus A, then as you can see it will have some, that means this is for 1, this is for 0, this is again for 1. So, the average value will have a DC. So, that DC component will not pass through the medium. So, that is why we shall try to do the encoding in such a way that DC component is not present. That means, we shall transform the SIG data into a form of signal which will not have DC component. Then comes the question of signal spectrum. Signal spectrum will play an important role because the bandwidth of the signal that you are trying to send through a medium will decide whether it will be distorted or not. That means, the bandwidth has to match with the transmission media. So, signal spectrum has to be taken into consideration when we do the encoding. Then noise immunity, whether the encoding that we do has higher noise immunity or not. As we have seen that some of the transmission media has got inherent noises, we have already discussed in the transmission impairment lecture. There we have seen that in presence of noise we have to transmit signal, and obviously if the encoding is done such that it has higher noise immunity, it will be beneficial. Then we can try to do encoding which will help us in detecting errors. Whenever the signal is sent through the communication media, because of various types of noises, there can be error is introduced in the signal. So, at the receiving end, if we can detect error because of the encoding use, that will be helpful. So, we shall look into it. Then comes the question of synchronizations. Synchronization, as we shall see, we shall be sending signal. Say this is sent by the transmitter. We want the same thing to be received at the receiving end, but if this position and is not matched, is not the receiver end must be able to identify when this is going from low to high or when it is going from high to low. That means, these positions has to be identified by at the other end. Usually, a clock is used at the transmitting end to generate the signal. Similarly, at the receiving end, a clock is used to regenerate the signal. Now, these two clocks may not have exactly same frequency. That may lead to a lot of synchronization. Not only they may not have the same frequency, their phases may also be different. So, it is necessary to synchronize them, and for the purpose of synchronization there are two alternatives. What can be done? The a separate line can be used, separate channel can be used for sending the clock to the receiver. Then the receiver can use that clock for receiving the data, but that is not really feasible because of high cost. So, commonly it is necessary to regenerate clock from the received data with the help of some special hardware such as phase lock loop. However, this regeneration of clock at the receiving end is possible only when the signal has got sufficient number of transitions. That means, say suppose you are sending a long sequence of 0 or a long sequence of 1. If the encoded signal do not have enough number of transitions, then the phase lock loop will not be able to regenerate the clock. So, it is necessary to have enough number of transitions in the signal for the purpose of synchronization. So, while doing encoding, we have to take into consideration this synchronization aspect. Finally, the cost of implementation we have to see, because ultimately you have to encode the signal with the help with minimum cost. So, these are the important characteristics you have to look into for encoding. Now, let us see what are the various line coding schemes that is commonly used. The line coding techniques can be broadly divided into three types: unipolar, polar and bipolar. So, these are the three basic schemes that is being used. The unipolar is the simplest. Here you have got the two voltage level. Essentially, by unipolar we mean uni means 1. So, you are sending only voltage of one polarity, say this one, say 2A, and here when you are not sending anything, that is considered to be a 0 volt. That means, when you are not sending anything, that is 0 volt, when you are sending something, that is 2A volt. So, only one polarity of one polarity signal you are sending, and when you are not sending, that is being considered as 0 volt. That is why, although you are sending of one polarity, but we may consider it two voltage levels. So, do not get confused whenever you say unipolar, at the same time two voltage level. Essentially, we are sending voltage of one polarity, but whenever the volt signal is not present, then we consider it 0. For example, for 1 we are sending a voltage of 2A, and when it is 0 we do not send anything. Similarly, for 2A again we send 2A voltage, and for 0 do not send anything. And for that means the data is represented by voltage level. That means 1 is a voltage level 2A, 0 is no voltage or no signal is being sent. So, that is how this unipolar encoding is done. Unipolar encoding has got the characteristic has the following characteristic. It uses only one polarity of voltage level, as I mentioned, and here the bit rate is same as the data rate. That means, the modulation rate or baud rate is same as the data rate. In other words, you have got only one signaling element per bit. Unfortunately, because of as you have seen, we are using signal of only one polarity. As a consequence, there will be DC component, or the average value of the signal that will be received at the other end will have DC. So, there will be DC component present in the signal. And as you can see from this signal, whenever you have got long sequences of zeros or long sequences of ones, only one signal level is transmitted or no signal is transmitted. In other words, there will be no transitions, and that will lead to loss of synchronization for long sequences of zeros and ones. So, this unipolar scheme is possibly the simplest, but it is obsolete. It is not used because of the limitation. For example, DC component present, this is a bad feature, loss of synchronization is a bad feature, and of course, data bit rate and data rate is same. We may not consider it good, but it is not definitely bad. But it is simple because it uses only one polarity of signal. Let us see what are the other schemes used. Polar schemes. In case of polar, essentially two voltage levels are used, one positive and the other one negative. So, we are using one positive voltage and one negative voltage, and the polar encoding scheme has got several alternatives like NRZ, non return to 0, RZ, return to 0, Manchester encoding, differential Manchester encoding. So, these are the four different encoding schemes available under polar encoding. Let us see, let us consider their features one after the other. Non return to 0, that is NRZ. In this particular case, as you can see from this diagram, voltage level is constant during a bit interval. That means, for 1, it has got two varieties, NRZ L and NRZ I. First, let us consider the NRZ L. In case of NRZ L, non return to 0, L stands for low level. That means, here it means that the 1 binary value 1 is represented by low level. As you can see here, binary value 1 is represented by low level minus A, and 0 is represented by high level plus A. So, here we are using signals of two polarity, plus A and minus A, plus A and minus A, and these two polarities are used to represent a binary 0 and 1. So, 1 is represented by a minus A polarity voltage, and 0 is represented by plus A. So, that means the signal levels, state of the data is represented by signal level, and that remains constant during a bit interval, as I mentioned. So, you see here, during the entire bit interval, the data is either plus A or minus A. So, when it is 1, it is minus A, when it is 0, it is plus A. Let us look at the other alternative, NRZ I, where I stands for inversion. Inversion. That means, here what we are doing in case of NRZ I, for each one the bits in the bit sequence, the signal level is inverted. Here, as you can see, this is a 1, for which it was minus A. Whenever a next A is encountered, it is you can see here it is making a transition from minus A to plus A. Another one is here. So, in this boundary again it is making transition from plus A to minus A. So, here there are two zeros, so there is no transition. So, whenever a 1 is encountered, the signal is making a transition from, or it is getting inverted from the previous signal level. So, here it was inverted from minus A to plus A, here it was inverted from plus A to minus A because of the presence of this one. Again, another one is encountered here, here it is inverted from minus A to plus A. So, this is how the transition from one voltage level to the other voltage level takes place in this particular case. In both the cases, as you can see, in the previous case, as you can see, whenever there is a transition from 1 to 0, then there is transition. That means, data changes from 1 to 0, there is a transition. Or in the next case, whenever consecutive ones are there, or a 1 is encountered, there is transitions. But whenever you have a long sequence of 0, then there is no transition in the signal, and that will lead to loss of synchronization. So, here are the characteristics of this NRZ encoding. Here you can see it has got two voltage levels, plus A and minus A. Here the bit rate is same as the data rate, because the number of signaling elements per bit is 1. So, data rate is same as the baud rate. So, in other words, here it is that M is equal to 2. The loss of synchronization for long sequences of 1s and 0s. So, whenever you send long sequence of 1 or long sequence of 0, you will find there will be loss of synchronization. And in this case, if you look at the signal spectrum, you will find most of the energy is concentrated between 0 and half the bit rate, as it is shown in this diagram. Here you find for NRZ I and NRZ L, it is represented in this signal spectrum is shown here. On the x axis you have got normalized frequency f by r, R is the bit rate, and mean square voltage per unit bandwidth. So here we find most of the energy uh, is uh, is in around this region, half of the bandwidth. That means this is one, this is the bandwidth of the signal. We can see here most of the energy is between DC and the middle point of the signal around 0.5. So here major part of the signal energy. So most of the energy is concentrated between 0 and half the bit rate. So this is the characteristics of NRZ spectrum, NRZ encoding both NRZ-L and NRZ-I. So synchronization has been found to be a major concern in the two schemes that we have discussed. On the other, to overcome that, we can use RZ encoding, that is known as return to 0. So here what we do, as you can see, for each bit there are it returns to 0. If it is 1, it is 1. If the data is 1, it is plus A. Then in the middle point of the bit, it returns to 0 and it remains there. And for 0, the signal value is minus A. Again, in the middle point, it returns to 0. So here we see for each bit there are two transitions. One is from low to high and another is low to high to low. So there are two transitions per bit is taking place irrespective of whether it is 0 or 1. So if you have long sequences of 0 or long sequences of 1, you will not face any difficulty because the number of transitions is quite large, and as a result it is very good for synchronization. However, it uses 3 levels of encoding. So it is possible to have, that means log 2 3, that the information content can be more, but unfortunately you are encoding only 2 data. That means we are that means the data rate is not increased, although it has the capability to have higher higher information rate. So however, the bit rate is double that of data rate because the number of transitions it is making. So it is not at all an efficient encoding. So here baud rate will be equal to 2 that of data rate because of, so this is definitely bad. The signal requires higher bandwidth than the data rate. However, it provides you good synchronization as you have seen, and the increase in bandwidth is the main limitation and concern. Because of this, the signal has got double the bandwidth than the data rate. Data rate is multiplied by 2 to the baud rate, and as a consequence RZ encoding is good from the viewpoint of synchronization, but it is bad from the viewpoint of the bandwidth requirement. Let us see how we can go for a better scheme, how we can make it little better. The this Manchester encoding is also a bipolar encoding. Here we are also using plus A and minus A, two signals of two polarity levels. However, as you can see, we can consider it that as if we are dividing into each signal element is divided into two phases, biphase, two phases, the first part and second part. So in Manchester encoding, what we are doing, there is a mid bit transition. So mid bit transition is taking place. So each mid bit transition, for example, for 1 it is the transition is from minus A to plus A. For 0 it is from plus A to minus A. So if the next bit is 1, then it has to go from minus A to plus A. So there is no need to transition in the middle. However, if the next bit is 1, here it will make transition from say low to high. In this middle position, it has to again make transition from low to high. So in the beginning it is making transition from high to low, so that it is possible to have low to high transition. That means whenever you have two consecutive ones, as you can see, the number of transitions will be low to high, high to low, then low to high. On the other hand, whenever you have got two consecutive zeros, again there will be transition from low to high, sorry, high to low, low to high, again from high to low. So, the number of transitions is more for consecutive ones and consecutive zeros. However, when you have got consecutives of zeros and ones, then as you can see the number of transitions is 1 per bit. However, you have got enough number of transitions. This is Manchester encoding, where the signal levels are represented by the number of transitions. I mean, essentially it is making from high to low or low to high in the middle bit position. Let us see the other one, the differential Manchester, which is known as biphase encoding. Here the presence of transition in the beginning of a bit position represents a 1. That means a transition in the beginning of a bit position, this is the beginning of a bit position, this is the beginning of a bit position, this is the beginning of a bit position. If it is a 0, then there is always a transition in the beginning. For example, here there is a transition, but it can be from high to low or low to high, there is no distinction. If it is 1, there is no transition. So, it depends essentially on the previous bit. For example, here this 1 for 1 or 0 in the middle there will be always transition which is used for synchronization purpose. That means, in the middle there is always transition. So, you can see here there is transition, here there is transition in the mid bit position. Only in the beginning there is transitions if it is a 0. So, this is a 0 bit. So, there is transition in the beginning. This is a 0 bit, there is a transition in the beginning. This is another 0 bit. So, there is transition in the beginning. So, for each of these bits, so there is transition here, here, here for all the zeros. On the other hand, there is transition in the middle for the purpose of synchronization. So, you can very easily recover data from this, and at the same time it will provide you very good synchronization. So, it has got two levels, two voltage level, plus A and minus A, as you have seen. There is no DC component, as you can see here. Alternately, you are making it high and low, high and low. So, the average value will be 0. So, there will be no DC component present. It is a very good feature, and it provides you very good synchronization, because number of transitions per bit element will be at least 1. There may be more than one transition in case of consecutive zeros or consecutive ones, but it gives you at least one transition. So, it gives you very good synchronization. However, the bandwidth is increased here. It gives you higher bandwidth due to doubling of bit rate with respect to data rate. That means, when you are sending a sequence of zeros and sequence of ones, then the bit rate is the data rate, I mean the baud rate is double than the data rate. So, that is a bad feature. Definitely this is not advantageous, but because of these two features, it is attractive and widely used in many encoding schemes, practical encoding schemes. Let us look at the bandwidth. Let us look at the bandwidth of these two signals, Manchester encoding and differential Manchester encoding, with respect to NRZ and NRZ. As you can see, in case of NRZ and NRZ, the bandwidth was very close to 0. On the other hand, for Manchester encoding, as you can see, there is no DC component, there is no signal component closer to DC 0 volt, and most of the energy is concentrated around the bit rate. So, 1. However, it spreads uh, uh, further. So, it can have higher signal components, higher frequency signal components for both the cases, and it gives you a some kind of band pass. I mean, it can be, as you can see, this can be very efficiently sent through a band pass channel, because the frequency spectrum has got higher frequency components around the middle, and on either side the frequency components are less. So, it is a very good frequency characteristics, except that the bandwidth requirement is higher. Now, let us focus on the bipolar encoding schemes. We have discussed unipolar and polar. Now, we are considering on focusing on bipolar encoding. In bipolar encoding, uh, we shall be using a technique known as amplitude mark inversion. This terminology mark has come from the day of telephony. In telephony, we used to send signals in the form of mark and space. So, that terminology has been borrowed here, and here the AMI is one kind of bipolar encoding, as we shall see. This is known as bipolar AMI. It uses 3 voltage levels. 3 voltage levels, these are plus A, 0 and minus A. So, as you can see, there are 3 voltage levels, plus A, minus A and 0. And unlike return to 0, the 0 level is used to represent 0 here. In case of RZ encoding, what we did, the 0 voltage level was not representing either 0 or 1. So, signal was returning to 0 both for 0 and for 1, but here it is not so. A 0 is represented by, that means a 0 voltage level represents a that means 0 data, 0 bit is represented by 0 volt. On the other hand, a 1 can have either positive voltage or negative voltage depending on I mean it alternately changes. For example, for this it is plus A, this one, next one will have minus A, next one will have plus A, next one will have minus A. So, that is why it is called alternating binary ones are having alternating positive and negative voltages. So, this alternating positive and negative voltages can be sensed to identify ones. However, if there is a long sequence of zeros, then obviously there will be no transition. So, this will again lead to loss of synchronization, as we shall see. So, here there is no DC component because it uses positive and negative. However, loss of synchronization occurs for long sequence of zeros, and as a consequence it gives you lesser bandwidth. Somewhat similar to bipolar AMI, we have got pseudo ternary. It is same as AMI, but alternating positive and negative pulses occur for binary 0 instead of binary 1. In the previous case, we have seen that alternating voltages are taking place for 1. In case of pseudo ternary, if we replace the ones by zeros and zeros by ones, it will be pseudo ternary. So, the characteristic will be same as bipolar AMI, not different characteristic, but that means the characteristics will be same as the bipolar AMI for pseudo ternary. That is why you have written it here, but only difference is that here binary 0, here binary 1 represents 0, and for 1 alternating positive and negative voltages. That is the difference between bipolar AMI and pseudo ternary. So, you can use either of the two having the same characteristics, and obviously this is a very good feature, no DC component. Unfortunately, loss of synchronization for long sequences of zeros has made it I mean not useful. However, it has a very attractive feature, lesser bandwidth, as we shall see in the subsequent diagrams. So, before we discuss compare the various techniques that we have discussed in this lecture, one important parameter I have already mentioned about it has to be taken into consideration, that is the data rate, and another is modulation rate. Modulation rate is expressed in terms of baud, BAUD, and data rate, as you know, it is expressed in terms of bits per second. Now, what is the relationship? Relationship between data rate and baud rate is data rate D is equal to R by B, where B is the number of bits per signal element. That means a signal element can have more than one bit, can represent more number of bits. or it can have less number of bits. So, depending on that, the data rate can be more or less. Say for example, if the uh, number of levels, L is the number of different signal elements, signal levels, actually it will not be signal elements, it will be signal levels. And if L is the number of signal levels that is being used, then the data rate will be more than the baud rate, R by B. R is the data rate, that means, and D is the modulation rate, that means R will be equal to D into log 2 L. That means the data rate R will be more whenever you are using more number of signal levels, as we shall see. And with this, because of this, the efficiency will be more whenever the data rate is more than the baud rate. Let us see what is the situation for the codes that we have discussed. So, this is the modulation rate. Minimum modulation rate for NRZ del is 0 0 0, both for NRZ del, NRZ I and bipolar AMI, because for that it does not change at all for some values zeros and ones. So, it is 0 for 1 0 1 0 alternating ones and zeros. For NRZ del it is 1, for NRZ I it is 0.05, and for bipolar AMI it is 1.0, for Manchester it is 1.0, for differential Manchester it is 1.5. And look at the maximum. The maximum occurs in case of differential Manchester, say 2.0, 2.0, both for Manchester and differential Manchester. And in case of, as you can see here, then from the viewpoint of modulation rate, we find that bipolar AMI has got good characteristic. On the other hand, the Manchester and differential Manchester requires higher modulation rate compared to the other two, compared to other schemes, and as a result they are not very attractive from this viewpoint. However, we have seen that Manchester and encoding gives you very good synchronization facility. That means whenever you are sending the signal, either a sequence of zeros, long sequence of zeros or long sequence of ones, it will not lead to synchronization failure, because at the other end the phase log loop will be able to regenerate the signal without any problem. If we compare the bandwidth of the different signals, we find that the NRZ L and NRZ I has got lower bandwidth. However, because of the presence of DC component and the low pass nature of the signal, it is not attractive. On the other hand, Manchester and differential Manchester encoding has got very good bandwidth spectrum shape. It has got most of the frequency components in the middle. However, it has got higher bandwidth. However, the AMI and pseudo ternary has got lesser bandwidth and it has got very good frequency spectrum. Most of the energy is centered around the middle of the frequency and there is no DC component, as you can see. So, this is the bandwidth comparison of the different encoding techniques that we have discussed. Of course, there are other special purpose codes that is being used in digital transmission. One is known as 2B1Q, 2 binary 1 ternary. So, this uses compared to polar or bipolar, it uses 4 voltage levels, in contrast to 2 voltage levels that is commonly used in polar. Here we see for 0 0 it has got minus 3 volt, for 1 1 plus 1.5 volt, for 0 1 minus 1.5 volt, for 1 0 plus 3 volt. So, we see here it has got 4 voltage levels. So, it gives you higher data rate. That means R is equal to D. If we look at the previous diagram, this one, that R is equal to R by B, that means R is will be equal to D into log 2 L. So, here R is equal to D into log 2 L. So, L here is 4. So, because it is using 4 levels, the data rate will be 2 times, and as a result each signal element will be able to represent 2 bits. So, 2 bits means this signal element minus 3 is representing 0 0, or this signal element that is plus 1.5 is representing 1 1. So, we see by using this multi-level encoding we are able to send more data with lesser number of signal elements. So, in other words, with lesser baud rate your data rate is more. So, however, because of larger number of signal levels, it will be more prone to error. So, signal to noise ratio of the medium has to be better, only then this can be used. Then there is another special purpose code that is used, is known as MTL3, multi-line transmission. Here also use 3 levels. It is very similar to NRZ-I. In case of NRZ-I, we have seen that we are using inversions, non-return to 0 inversions, but instead of 2 levels, here we are using 3 levels. So, here we see signal transition occurs at the beginning of each bit, signal transition occurs at the beginning of each one bit. So, whenever it is a 1, it is making a transition from 0 to 1, and here also it is making a transition from 0 to 1, 1 to 0. So, here we can see we are using say 0 to plus 1, then plus 1 to 0, again from 0 to minus 1. So, in this way it is using 3 voltage levels, and signal transition is occurring at the beginning of each one. So, it is very similar to NRZ-I, but uses 3 different levels. That is the basic difference that is used at the beginning of each bit, each one bit. That is the characteristic of this code. Now, we have seen that bipolar AMI has got very good characteristic, but unfortunately it has got the bad signal characteristic. So, the signal characteristic that is bandwidth characteristic is bad, which can be improved by a technique known as scrambling scheme. So, this can be considered as extension of bipolar AMI, particularly when we are sending signal over a long distance. Bandwidth of the channel is very precious. When it is for short distance communication like local area network, then bandwidth is not really very important. On the other hand, whenever we are sending over a long distance, bandwidth has to be very judiciously utilized. In such cases, we shall go for this kind of special schemes and try to develop better utilization of the bandwidth. And some of the characteristics of these special encoding codes are no DC component, no long sequence of 0 level line signal. That means, whenever there is long sequences of 0 level, we shall try to forcibly introduce some transition. However, with minimum increase in bandwidth, I will not say no, with minimum increase in bandwidth, as we shall see in the next lecture. Then it should have some error detection capability. Examples of such scrambling schemes are B8ZS and HDB3, which we shall discuss in the next lecture. So, in today's lecture we have discussed about several schemes like NRZ, RZ and bipolar schemes, and here are some of the review questions. Why do you need encoding of data before sending over a media? First question. Second question is, what are the 4 possible encoding techniques? Give examples. Third question is, between RZ and NRZ encoding techniques, which requires higher bandwidth and why? Fourth question is, how Manchester encoding helps in achieving better synchronization? Here are the answers to the questions of lecture 5. On what parameters the quality of transmission depends in case of transmission through unguided media? Answer is, in case of unguided media, the transmission quality primarily depends on the size and shape of the antenna and bandwidth of the signal transmitted. So, we have already discussed in detail the unguided media. There we have seen the size and shape of the antenna, and the bandwidth of the signal that we are sending will play important role. Second question was, what are the factors responsible for attenuation in case of terrestrial microwave communication? We have seen the attenuation characteristic is represented by the formula 10 log 4 pi d by lambda square. So, it depends on the distance. The attenuation increases at the rate of distance square. However, the attenuation also increases with frequency or inversely proportional to lambda square. However, moreover, during rainfall attenuation is less if there is no rain. So, in other words, when there is rain, attenuation is more. Third question was, what parameters decide the spacing of repeaters in case of terrestrial microwave communication? The parameters are the height of the antenna h and the adjustment factor k based on this relationship 7.14 root kh, where d is the distance in kilometer between the two antennas, and based on this one can, based on the height of the antenna used, one can calculate the distance, and usually the k value of k as you know is equal to 4 by 3 that can be used to compute the distance. Fourth question was, why two separate frequencies are used for uplink and downlink transmission in case of satellite communication? As I mentioned in the lecture, two separate frequencies are used so that one cannot interfere with the other and full duplex communication is possible. If we use same frequencies, then there will be interference and we cannot have full duplex communication. So, to achieve full duplex communication, two separate frequencies are used. Fifth, last question was, why uplink frequencies are higher than the downlink frequencies in case of satellite communication? The reason I mentioned was the satellite gets power from solar cell. So, the transmitter is not being of higher power because it is taking power from the solar cell. On the other hand, the ground station can have much higher power. As we want less attenuation and better signal to noise ratio, lower frequency is more suitable for downlink and higher frequency is commonly used for uplink. So, this is the answer to the question number 5. That was the last question. Thank you. Hello viewers, welcome to today's lecture on transmission of digital signal. This is the second lecture on this topic. In this lecture, we shall cover these following topics. First, I shall give a brief introduction. This will be followed by scrambling coding schemes. Then we shall discuss basic concepts of block coding steps, conversion of analog data to digital signal. This will be a different type. Then two basic approaches of analog data to digital signal, that is pulse code modulation and delta modulation. Then we shall discuss limitations of pulse code modulation and delta modulation. Then compare these two approaches. And on completion of this lecture, the students will be able to explain scrambling coding schemes, explain the need for block coding, explain the cooperation of block coding. The students will be able to explain the coding techniques used for conversion of analog data to digital signal. They will be able to distinguish between the coding techniques such as PCM and DM, which are used for coding from analog data to digital signal, conversion of analog data to digital signal. Then they will be able to compare the advantages and limitations of pulse code modulation and delta modulation. So, here we now change gear from digital data to digital signal to analog data to digital signal. There are many situations where we have to send analog data, but we want to send in digital form, or we want to send in the form of digital signal, because sending that signal in the digital form has many advantages from the viewpoint of signal to noise ratio and other things. For example, analog data such as voice, video and music are to be converted into digital signal for communication through transmission media. One example is, say, voice that is being sent through telephone line. So, here we are trying to send analog data, but as you know, in modern telephony it is not sent in analog form, it is converted into digital form. So, digital signal is transmitted. Similarly, video and voice, video and music can be sent. And for that purpose, there are two basic approaches. The two basic approaches are, first one is known as pulse code modulation and second one is known as delta modulation. So, in this lecture today we shall discuss about these two schemes, pulse code modulation and delta modulation, one after the other. Let us first concentrate on pulse code modulation. The pulse code modulation has got three basic steps: sampling, quantization and line coding. Suppose this is the analog signal. So, this analog signal has to be converted into digital form for sending through a transmission media. First step is known as quantization, or first step is known as sampling. The sampling process converts the analog data, analog signal, you can say this is essentially analog signal, into a form known as pulse amplitude modulations. First question is, why B8ZS coding is preferred over Manchester encoding for long distance communication? That is the first question. Second question is, why is it necessary to limit the band of a signal, bandwidth of a signal before performing sampling? So, here it will be bandwidth of a signal before performing sampling. Third question is, distinguish between PAM and PCM signals. So, pulse amplitude modulated signal and pulse code modulated signals. What is the difference between the two? Third question. Fourth question is, what is quantization error? How can it be reduced? Obviously, we are referring this question with respect to PCM. Fifth question is, explain how and in what situation differential PCM performs better than PCM. So, this is the fifth question, which will be answered in the next lecture.